Hi, Dan Fleisch again. This is a video for section 1.1 of A Student's Guide to the Schrödinger Equation. This section is all about the basics of vectors. I explain in this first paragraph here why I think it's important to lead off with vectors when you're studying quantum mechanics. I know this is a review for a lot of you, but the idea is this. Just as vectors can be expanded in terms of components and basis vectors, so can the wave functions that are the solutions to the Schrödinger equation. And it's been my experience that students who get vectors are much more likely to understand the fundamentals of quantum mechanics. So this starts off with a vector A expanded in the Cartesian coordinate system. That is, using the Cartesian basis vectors I hat, j hat, and k hat. And here, the vector A is written as the sum of those three components. By the way, some people call the a sub x and the a sub y and the a sub z the components. Other people call those the coefficients, whereas the whole thing with the unit vector they call the components. You can use whichever convention you'd like as long as you understand that the vector A exists independently of how you expand it. You can expand it in Cartesian coordinates or in polar coordinates or in cylindrical coordinates, and it's the same vector. There's a little diagram of vector A on the next page. You can see the basis vectors pointing along their respective axes, and you can see the components, or coefficients if you prefer, ax, ay, az, telling you how many of those basis vectors are contained in the vector A. There's another way of thinking of the basis vectors given here. If you have, for example, 5i hat minus 2j hat and plus 3k hat, you can think of the component as telling you how many steps to take in the direction of that basis vector. That is, in this case, 5 steps in the x direction minus 2 steps in the y direction plus 3 steps in the z direction. The magnitude, also called the length or norm of a vector, pretty easy to find. Simply square each of the components, add them all together, take the square root. Notice that the length or norm is written with absolute value signs around it. And that the vector minus a has the same length as a, it just points in the opposite direction. Then there's a little bit about adding vectors. Here's how you add them algebraically. You add the x parts, you add the y parts, you add the z parts. Basis vectors don't get changed by this, and now you have a new vector c, which is the sum of vectors a and b. Also, you can multiply a vector by a scalar. If we multiply the scalar alpha times vector a, you can see that it just distributes along each of the three components, and you get this. What does that do to the magnitude? Well, if I multiply each of these by alpha, there we go, add them all together, the alpha squared comes out. You change the length, not the direction. There's another way to add vectors, by the way, and that's graphically, and that's shown here. By the way, this means this is an interactive graph, so if you've got the app, you can actually see this in action. In this case, we take one of the vectors, I picked b, and we displace it along a. So its tail just rides along a from the beginning to the end, and then the displaced b is over here. We haven't changed its magnitude or its direction as we displaced it. Then we draw a new vector from the beginning of the first one, a in this case, to the end of the second one, b in this case, and you get the sum of those two vectors. C is a plus b. We could have done that same thing by displacing a up here. That's why this is called the parallelogram rule. This just shows how you get the x components to add up. This one showed how you get the y components to add up. So as I said, this is relevant to quantum mechanics because in quantum mechanics, the solutions to the Schrödinger equation are going to turn out to behave like what we call generalized higher dimensional vectors. So you can add them together, you can multiply them by scalars, and without changing their direction. And how can a function have a length or a direction? We're going to get to that in chapter 2. There's also several ways to multiply vectors. Here's one. This is called the scalar or dot product. You've probably run into this if you've taken any kind of physics class. Notice the dot product of a and b. By the way, that can be written as a dot b. That's probably how you've seen it written before. In quantum mechanics, we have a little different notation. Sometimes it's a comma b. Means the same thing. If you take the dot product between two vectors, you get the magnitude of one times the magnitude of the other times the cosine of the angle between them. In the Cartesian coordinates, that's particularly simple to find because you can simply multiply the x components, the y components, the z components, and add them together. If the vectors are parallel, the angle between them is 0, cosine of 0 is 1, so you simply get the dot product equaling the product of their lengths. But if they're perpendicular, this is critical in quantum mechanics. If they're perpendicular, the cosine of the angle is 0 because 90-degree cosine is 0. So therefore, the scalar product between two vectors that are perpendicular is 0. That's one way we're going to define two objects as being perpendicular when we generalize all this. And if you dot a vector into itself, you get its magnitude times the cosine of 0. You get the square of its magnitude. So that's how the math works. What does all this really mean? The dot product, or its generalized version called the inner product. Well, as it says here, the dot product projects one of the vectors onto the direction of the other. So it gives you an indication of how much of, for example, B lies along the direction of A. Or you can go the other way and say how much of A lies along the direction of B. Now, as I acknowledge here in the footnote, you may have trouble saying, wait a minute, how does A and B, they don't lie along the same line at all. No, but imagine that this is east, say, and this is north. The question is this: in going from the beginning to the end of B, how far along the direction of A have I gotten? Well, B is northeast, and you do, when you go along B, get some distance east. You also get north, but what the dot product tells you is how much you get along the direction of A by going from the start to the end of vector B. You can go the other way, by the way. You can project A down to B and say, how much does A go along the direction of B? Once you multiply that projection by the magnitude of B, you'll get the same answer. So that's what the dot product means. Sometimes I use the phrase, how much one vector contributes to the direction of the other. Here's a nice little trick. If you want to know the cosine of the angle between the two vectors, you can take their dot product, divide by the product of their lengths. That's shown here. That cancels, and it leaves you the cosine of the angle, so you can find out the angle between two vectors simply through this process. This shows you what happens if you dot a unit vector into itself. Remember, a unit vector has a length of 1, so magnitude of 1 times magnitude of 1 times the cosine of 0, those are all 1, you get 1. I hat dot I hat is 1, as is j hat dot j hat and k hat dot k hat. Each of these unit vector lies entirely along itself, if you will. But when you dot the unit vectors into different unit vectors, I hat dot j hat, for example, none of I hat lies along j hat. They're perpendicular. That's why the cosine gives you 0. And therefore, each of those unit vectors dotted into one of the others, not itself, gives you 0. The reason I mention that is because you can use this little trick to find the components of a vector. If you want to know a sub x and you know a and you know the I hat basis vector, you can form that dot product and look at what's going to happen. I hat dot I hat is going to give you 1, whereas I hat dot j hat and I hat dot k hat are going to give you 0. So what survives is just that. That's how you find the x component, by dotting the x basis vector into the vector you have, a. Same thing for the y part, same thing for the z part. One thing I didn't say is these vectors are called a complete set. In addition to ortho, because they're perpendicular, normal, because they have unit length, they are also a complete set. You can make up any vector in three-dimensional Cartesian space by weighted combinations of these three basis vectors. So, main ideas are summarized here. As I said in the preface, in the first two chapters, you're going to find these little blocks of main ideas just to make sure you're tracking what's going on here. They are: vectors are mathematical representations of quantities that can be expanded as components and directional indicators. You can add them together, you can multiply by a scalar, you can form this thing called the dot or scalar product, and you can use that to find the components of a vector. Here's one of those relevance to quantum mechanics boxes that I mentioned. Just as vectors can be expressed as weighted combinations of basis vectors, the quantum wave functions, the things that are solutions to the Schrödinger equation, can be expressed as weighted combination of basis functions. A generalized version of the dot product called the inner product We're going to use that to calculate how much of each of these component wave function contributes to the sum. That's going to turn out to be helpful when we make a measurement of a quantum parameter. It's going to help us determine the probability of a given outcome. All right, that's it for this section. If you're interested in Dirac notation, that's up next.